You sleep soundly, don't you? You cruise at 80 miles per hour across a steel and concrete bridge that cost $2 billion, listening to your little podcast with the arrogant certainty that modern engineering is protecting your life. You look at those suspension cables, thick as tree trunks, and you think, that is indestructible. Physics is laughing in your face. The truth, which the millionaire consortiums prefer to hide under a mountain of structural jargon and computer models, is that nature doesn't need a cinematic hurricane to vaporize your bridge or your corporate tower. It only needs patience and rhythm. Today, I am going to rub it in your face how the wind, a simple, steady breeze that barely messes up your hair, hunts, chews up, and turns the toughest structural steel on the planet into pathetic red dust. And the most humiliating detail for the geniuses who designed these modern marvels? I will prove to you exactly how the catastrophic collapse of these megastructures happens using nothing but a cheap rubber band. Be as offended as you want, but physics has no mercy for your tight budgets or your false sense of security. Pay attention. Look at the blueprints of any modern infrastructure disaster. The architects and the board of directors always pop champagne over the exact same word: optimization. They look at a massive, heavy, old-school structure and say, we can do this cheaper, lighter, and sleeker. So, they strip away the bulk. They swap out thick, dumb iron for ultra-high-strength steel or aerospace-grade aluminum. They design these incredibly slender suspension hangers, towering turbine shafts, and perfectly smooth architectural masts. The computer software spits out a green check mark. The simulation promises that the maximum force from a normal wind gust is a tiny, laughable fraction of the metal's yield strength. The engineers pat each other on the back, completely convinced they have outsmarted nature. They brag to the press about aerodynamic efficiency and the myth of infinite fatigue life. But here is the punchline. That exact celebrated genius is the trap. By making the structure lighter, thinner, and more flexible, they didn't just save millions of dollars in material costs. They inadvertently built a gigantic, multi-million-dollar tuning fork. The old, heavy, brutally over-engineered bridges of the past were simply too fat and clumsy to vibrate. But these new, sleek, optimized masterpieces, they are mathematically desperate to resonate. The engineers were so blindly obsessed with surviving a once-in-a-century hurricane that they completely ignored what a gentle 15-mile-per-hour crosswind could do on a random Tuesday afternoon. By trying to be modern, they handed the invisible predator the exact acoustic instrument it needed to start the slaughter. Let's do an experiment. Go to your kitchen drawer, grab a thick rubber band, and hold it against your upper lip. It feels like room temperature, right? Now, pinch the ends and stretch it as hard and as fast as you can, and immediately touch it to your lip again. It is warm, almost hot. Now let it snap back. It instantly feels cold. Congratulations! You just performed a thermodynamic experiment that explains why that $2 billion suspension bridge is currently trying to kill you. When you stretch that rubber band, you are forcing its chaotic, tangled internal molecules to line up perfectly. That takes energy, and the material sweats out that effort as physical heat. When you let go, it absorbs heat from the air to scramble itself back into a messy, high-entropy pile. Now, imagine you sit there, stretching and releasing that same rubber band, over and over, 5 times a second, for an hour. What happens? It does not stay stretchy forever. The heat builds up inside it due to the continuous dissipation of energy. The microscopic bonds holding the rubber together begin to snap permanently. Tiny, invisible tears form. Eventually, with barely any effort at all on your part, the rubber band becomes brittle, snaps in half, and stings your fingers. Steel, that magical, indestructible metal that holds up our civilization, is just a very stiff, very stubborn rubber band. When a steady, low-velocity wind hits a slender bridge hanger or a towering light pole, it does not just push it over. The air separates around the cylindrical shape, creating alternating suction vortexes on the left side, then the right side, then the left side again. The wind pushes and pulls the steel, vibrating it exactly like you stretching and releasing that rubber band. To your naked eye, the steel structure is perfectly still. But under a microscope, the crystalline lattice of the metal is being stretched and compressed millions of times. And, just like the rubber band, the steel cannot perfectly absorb and release all that kinetic energy. It loses a tiny fraction of it as heat. Engineers call this hysteresis, but let us just call it what it is. The metal is sweating, baking itself at a microscopic level. Because of this localized stress, the steel at the sharp corners, the welded joints, and the bolted connections starts to harden and turn brittle. The crystalline layers inside the metal start slipping past each other, creating microscopic fault lines. And then, the real horror begins. As the wind vibrates these massive bolted steel plates against one another, they do not move inches. They move by fractions of a millimeter. This microscopic rubbing forcefully grinds away the protective outer layer of the steel. The raw iron underneath is exposed to the oxygen in the air, instantly oxidizes, and the very next vibration scrapes that microscopic rust layer right off. The wind literally grinds the solid steel into a fine, highly abrasive red powder. It looks just like rust, but it is not from rain. It is from pure friction, a process known as fretting corrosion. Inspectors call it rouge, or simply red dust. When you see red dust bleeding out of a bolted joint or a heavy wire cable, you are looking at the pulverized, cremated remains of what used to be structural integrity. The wind has chewed the metal into a powder, using that very powder like sandpaper to dig deeper, microscopic pits into the steel. From there, a crack forms. And once a crack forms in fatigued steel, the wind has already won. Nature does not assassinate a multi-billion-dollar structure in the dark. It leaves a trail of evidence. It practically sends an engraved invitation to the funeral. But the people in the hard hats, armed with their fancy tablets and advanced degrees, are entirely too arrogant to read it. They ignored the 3 inescapable warnings that the invisible predator was already inside the house, actively chewing on the foundations. Warning number 1. The Song of the Executioner. Have you ever stood near a tall aluminum light mast, a transmission tower, or a suspension bridge cable on a perfectly calm, sunny day, and heard a low, steady hum? Tourists think it is poetic. They think it is just the wind whistling through the wires. It is not. That audible hum is the sound of second-mode aeolian vibration. It is the structure achieving aerodynamic lock-in. The steel is not simply being pushed by the wind, it is actively resonating. Every single time you hear that hum, the metal is being violently stretched and compressed 5 to 20 times a second. It is the exact sound of thermodynamic energy baking the crystalline lattice of the steel. The bridge is literally screaming, but the engineers look at their anemometers, see a gentle 15-mile-per-hour breeze, and write normal environmental noise in their pristine little notebooks. Warning number 2. The red bleed. This one is almost a bad joke. When inspectors climb up to check the massive, slip-critical bolted joints holding these towers and hangars together, they frequently find a fine, powdery red substance smeared around the steel plates and the heavy wire ropes. Ask an average maintenance contractor, and he will shrug and say, "Oh, it's just a little surface rust from the rain. Nothing a little paint won't fix." Wrong. It is not water rust. It is fretting corrosion. Because the structure is constantly humming, those massive steel plates are rubbing against each other by invisible fractions of a millimeter. That microscopic, relentless sliding violently scrapes away the metal, exposing raw iron, which oxidizes instantly and then gets ground down again on the very next vibration. That red dust is the pulverized, cremated remains of the structural steel. The bridge is bleeding its own powdered bones. The wind has turned the indestructible metal into an abrasive powder, and it uses that very powder like a grinding paste to dig fatal micro-pits into the joint. And the inspectors literally wipe it away with a rag and sign the safety clipboard. Warning number 3, the green light of death. If you walk into the control room of any modern megastructure, you will see monitors displaying real-time sensor data. The stress sensors are reading the tension in the steel. The computers are looking at the ambient wind speed and comparing it to the steel's ultimate tensile strength. The software calculates the load, sees that it is only sitting at a laughable 5% of the structural capacity, and flashes a comforting bright green light. Safe. Infinite fatigue life. This is the ultimate trap of human arrogance. The computer is completely blind to microscopic fatigue. It assumes that if a 15-mile-per-hour wind doesn't break the steel today, it won't break it after 10 million cycles either. The algorithm completely ignores that the localized stress hidden at the microscopic edge of a bolt hole is already tearing the atomic bonds apart. The sensors tell the board of directors that the structure is invincible, while deep inside the metal, a smooth, polished fatigue crack is silently slicing through the core. They trust the glowing green screen, while the physics of the rubber band prepares to snap the spine of their masterpiece. The aftermath is always exactly the same. The multi-billion-dollar structure collapses in a fraction of a second. The remaining uncracked cross-section of the steel, now violently chewed away by the wind and too weak to hold even its own dead weight, shatters like cheap glass. Cars plunge into the water. Infrastructure is severed. Billions of dollars are instantly vaporized, turning into a twisted graveyard of scrap metal and, of course, a lingering cloud of fine, red dust. Then come the press conferences. The exact same executives and lead engineers who previously bragged to the media about their highly optimized, ultra-lightweight, cost-saving designs now stand behind wooden podiums, looking appropriately devastated. They will look right into the cameras and blame an unprecedented weather event. They will call it an unforeseeable anomaly. They will hire expensive PR firms to convince you, and the families of the victims, that this was just a tragic, freak accident. Do not believe a single word of it. There was absolutely nothing freak or unforeseeable about the collapse. The math was always there, ticking away, cycle by cycle, vibration by vibration. The tragedy was never the wind. The true tragedy was the staggering, lethal arrogance of men who actually thought they could negotiate with thermodynamics. They tried to outsmart nature to save a few $1 million on raw materials and construction time, entirely forgetting the most brutal law of the universe. Physics does not read spreadsheets. It does not respect political deadlines. It cannot be bribed, and it absolutely does not care about your corporate profit margins. So the next time you drive across a gleaming modern suspension bridge or park under a massive steel light mast, turn off your music and roll down your window. Listen closely. If you hear that low, steady hum vibrating through the air, do not mistake it for the harmless whistling of the wind. You are listening to the sound of a giant metallic rubber band being stretched to its absolute breaking point. And eventually, physics always lets go.